Folks. Welcome to virtual 4130 for the day. So the last time we talked, like I said, I got a bit off the path that I wanted to be on, but we spent some good time talking about essentially splitting fields. We talked about, how to get a field extension where a polynomial has all its roots. And we talked about the nature of Galois, what it means for an extension to be Galois. Let me go ahead and give you the biggie. This is the fundamental theorem of Galois theory. Of Galois theory. Okay, so here's the setup here. By the way, you can see this stated in different ways, and there's different kind of twists on it. Here's the version we're going to go with. If this extension is finite and Galois, so f over k, f is a finite extension in Galois. And let me also point out, just so we're on the same page here, since this extension is finite, it has to be algebraic, right? Then there's a one-to-one correspondence. There exists a one-to-one correspondence between intermediate fields of the extension f over k and subgroups of the Galois group. G. So I'm going to use the terminology instead of writing the Galois group f over k. That'll just be G. And this is given by how does this correspondence work? Here, this E here is a field. It's intermediate to F. This goes to its prime. And let me remind you what this is. This is the set of sigma in G, Galois group, such that sigma E equals E for all E and E. So let me point out that these are all the automorphisms of F. So it's in the Galois group F over K. These are all the automorphisms of F that fix E. So another way to put this is the Galois group of F over E, because now E is being fixed. Here in G, K is the fixed field because this is a Galois extension. So the only thing fixed by all of G is K. And now what you have for E, this is just the automorphisms that fix E. So it's a smaller, potentially smaller set. Such that I've got a couple of properties that hold. Number one, if L inside M are intermediate fields, then the degree of M over L, so if you measure how big M is as an extension field of L, this is exactly equal to the index of M prime and L prime. So when you Right, it's the index of M prime and L prime. So in particular, if this is Galois, this is the degree of the extension, the whole extension F over K. This should be K prime over F prime. Right? But K prime is, well, so this is the index of G, because K prime, this is the set of everything in the Galois group that fixes K, which is everything in the Galois group. And F prime, this is everything that fixes the Galois group. I'm sorry, this is everything that fixes the entire field, which is just one. So in other words, the degree of extension is equal to the order of the Galois group. So in particular, if you have, if you know that F over K is Galois and the extension is of degree, say 10, right? Then you know for a fact that the Galois group has 10 elements in it. It's a group of order 10. Number B, F is Galois over every intermediate extension. So F is Galois not only over K, but it's also Galois over every intermediate field between. So if E is between K and F, then F is also Galois over E. It's not necessarily true that E is Galois over K. Well, if E is an intermediate extension, then E is Galois over K if and only if E prime is a normal subgroup of G. So that is the Galois group of F over E is normal in the Galois group of G of F over K. So it's not always true, well, it's not always necessarily true that E is Galois, an intermediate field is Galois over the base field. Of course, it certainly is sometimes, like, for example, if the Galois group is abelian, then every subgroup is normal, things like this. But this is a condition needed. E is Galois over the base field if and only if E prime is normal in K prime. And of course, I know you're dying to ask this, because when you have a normal subgroup, and this is why I wrote it in this notation here for this past business, if this thing is normal in this, then I can quotient it out. So I have Galois group of F over K modulo the Galois group of F over E. So if this is normal in this is isomorphic to the Galois group of E over K. Which works really nice for the symbolism, but we're going to have to see why that's true. Let me give you, I'm going to go back. So, well, fortunately, this is all on it's on video, so I guess you can pause it and stare at it and bask in its beauty. But so this is the big thing about Galois, and this, I'm gonna go back to the example we did before, kind of take a look at it again. There's a one-to-one correspondence, so intermediate fields between K and F, they pair up the one-to-one correspondence with the subgroups, the Galois group, and the normal ones have a special place. So the degrees of the extension are the same thing as the index of the primed fields, and this is really highlights the special part about the normal. F is Galois over every intermediate extension, but for intermediate to be Galois over the base field, it's got to correspond to a normal subgroup of the Galois group, and you get this quotient here. So let me kind of do a schematic here because I think that would be good for the soul. If you look back at our example from earlier, if we look back at our example from earlier, then here I'm gonna let F be Q alpha omega, where alpha is the real cube root of 2, and omega is the primitive cube root of unity, a primitive cube root of unity, I should say. So recall that omega squared equals omega bar is omega inverse, and omega squared plus omega plus 1 equals 0. Now, we had these fields here. And let's see, I corresponded for the fields. Okay, so I'm going to start with the fields here. So we have Q down here. This is Q alpha. And this. And we had, oh, actually, I want to do Q omega here. Do omega over here. Do the kind of triplet over here. Q alpha, Q alpha omega, Q alpha omega squared. So what the fundamental theorem of Galois theory says is, hey, I can make a diagram that looks just like this by priming this. All right. So if I do the prime to this, oh, and by the way, my Galois group here, going back to the example, F over Q consists of the identity sigma 1, 2, sigma, or whatever that dang letter is, phi of 2, 3, phi of 1, 2, 3, and phi of 1, 3, 2. Like that. These are the ones from that table that we did. Okay, so when we apply the prime, the one-to-one correspondence, here's what we get. We're going to get an exhaustive list of the Galois group. Okay, F prime, this is the set of everything in the Galois group that fixes everything here. Well, that's just the identity. If you look at Q omega prime, this is everything that fixes omega prime, or I'm sorry, that fixes this intermediate extension. So really for this one, it's a little bit easier. If you look back in your table in the notes, when I first did this example, if you look at what is what freezes omega, it's the identity, of course, and these two right here. So this was the identity, P 1, 2, 3, P 1, 3, 2. These are the set of automorphisms that fix everything in Q omega, because these are the three automorphisms that don't move omega at all, right? Notice that this is a subgroup of, this is a group of order 3. Let's do Q prime. This is the set of automorphisms in the Galois group that fix Q. Well, they all do. So this is all of S3. I'm not going to write all those mess now. But notice what happens here is the index here is 3, and the index here is 2, because it's a group of order 3, group of order 6, so index 2. This is exactly what happens here. This is a quadratic extension of Q, because its minimal polynomial is in fact quadratic. It's the irreducible polynomial, x squared plus x plus 1, irreducible for Q. And this extension right here is 3. We made an argument similar to this before, but the minimal polynomial over this, x cubed minus 2, this is of degree 3. The extra omega here doesn't help you factor x cubed minus 2. Certain sense? And for these other ones, they're kind of similar. If you look at Q alpha, well, so what fixes alpha? I think this one was the complex conjugation one. So I think that's probably 2, 3 actually. If you look back in the table, the only automorphism that fixes alpha itself is V2, 3. This index here is 3 because it's a subgroup of order 2 inside this group of order 6. And of course, the index here is 2 because this is a group of order 2, and that's the identity. And that's exactly what happens here, because we've already seen that this extension is 3, just like we got that index. And this is 2 because notice that the cube root of 2, notice that omega is not in here, right? Because this is actually not real, so it's not here. And its minimal polynomial has to have degree 2, because that's the minimal polynomial over Q, so it's no less over this. And so in a similar vein, filling out the rest of the table here, you get this. And that's how the fundamental theorem of, that's how this works. I could add one more thing here. This is isomorphic. So Q alpha omega prime and Q alpha omega squared prime. And I won't fill in the rest of this. But let me make one more remark here. It's fairly, let me kind of make the remark that F is Galois over every intermediate extension. Remember, to be Galois over a field, there has to be something, so to be Galois over some smaller field, there has to be something in this field that's not in the smaller field that is moved by an automorphism, right? Well, okay, so why is this thing Galois over Q omega? Well, just take something in alpha, just take, for example, alpha, right? That's an element of here that's not here. And there is certainly an automorphism of this field that takes alpha somewhere else, because there's an automorphism that takes alpha to alpha omega, and there you go. So this thing is Galois over over this one, right? Right. So to be Galois over this, there has to be something here that's moved by some automorphism. Well, here's a good one right here. Omega is here, but not here. And there's an automorphism of F that moves omega, namely complex conjugation, right? Right. And so forth. You can find something, you can do a similar thing here, find something here, and an automorphism that moves this and fixes the field here. And of course, all these examples, of course, show that it's Galois over this. Now, notice that this is the only normal subgroup other than the identity in the whole group. So this one right here, Q omega, is the only, it's the only intermediate field that corresponds to a normal subgroup. Now, notice this extension is of degree 2. And last time in class, we looked pretty extensively at this. In fact, and I'll give you, this field is actually equal to Q adjoining with the square root -3, right? And it's basically because of this here. If you contain omega, multiply this by 2 and add 1, and you've got the square root of -3. And if you got the square root of -3, you've got omega. And notice we gave an argument last time why these things have to be Galois over Q. So this is indeed Galois, and it corresponds to the fact that this is normal. And these things are not normal, right? And we've seen again that these extensions here are not Galois. Because, for example, any automorphism of Q alpha fixing Q has to take alpha to another root. But the other roots are outside of there, so you're stuck with only the alpha. Okay, so let's kind of, once again, a look at how that diagram works and sort of what's going on in the heartbeat. I'm going to go through some details here. I don't know how in the weeds I'm going to get, but we're going to at least kind of go through some of the major bits of why this theorem should be true, because it is a beautiful and powerful theorem. So let's start off with kind of a utility lemma, where we talk about sort of how these field extensions, how they're, what their interplay is with the primes, how the fields interact. Interact's not the right word, but how they correspond with the groups. So lemma. To 2.8. Let K and F be Galois. And LM intermediate fields. So at the outset, I'm not assuming that, I guess I probably should have. L and M are just intermediate fields. So both of them are between K and F. Let G be the Galois group and H and N be subgroups. F of K and H in subgroups of G. Okay. Number A, F prime is 1. And K prime is G. B, 1 prime is F. C, if L is an M, then M prime is an L prime. So that's interesting enough. Note when you prime these things, and there's a lot of things in mathematics that does this kind of thing. When you prime these things, it reverses containment. We'll see why that's true in a moment. If H is contained in N, so H is a subgroup of N, then again, the fields reverse things. that is the fixed field of M is contained in the fixed field of H. E, it's over here. L is contained in its double prime. And H is contained in its double. So notice, of course, when you start with the field L, you prime it, you get a group, you prime that back, you get a field. That field will contain the original. Same thing here. You start with H, you prime it, you get a field. Prime it again, a group that contains the original. And F, L prime is equal to L triple prime, and H prime is equal to H triple prime. Okay, let's go through some of this. A and B, I can probably kind of talk through. F prime, well, that's the set of automorphisms that fix everything in. Oh, right. So F prime is a set of automorphisms of F that fix all of F, right? And the only automorphism of F that fixes F, all of F, is just the identity, right? So no problem there. On the other hand, if you look at K prime, this is the set of everything that fixes K prime, and that's G by definition, because Galois group of F over K, that means by definition that K is fixed by everything in G. So this is kind of no sweat. 1 prime is F. So 1 prime is the set of everything in F that is fixed by 1. Okay, so all of F. That wasn't too bad. Let's look at C. Suppose that you have an L inside of M. We need to show that M prime is an L. So suppose sigma is in M prime. You know, I think I'm going to find myself writing these definitions again, just so I can kind of get this straight in my head. Now, what is M prime? This is a set of sigma in the Galois group, such that sigma M equals M for all M and M. Ah, okay, so I see. So if sigma is in M prime, it fixes everything in big guy. Well, if it's going to fix everything in big guy, it's got to be fixing everything in little guy too. So as L is contained in M, sigma of L equals L for all L and L. So sigma is in L prime. Therefore, L prime is, I'm sorry, oops, M prime is a subgroup of L. Ooh, I bet this is going to be the same, similar, right? Now we start from the group theoretic perspective. Suppose H is a subgroup of N. Now let's see, suppose X is in N prime. And of course, again, let's see, what does this mean here? N prime is a set of V and F such that sigma V equals V for all sigma in N. Okay, so this means that X is fixed. So X living here means that that means that sigma X equals X. For all sigma in N. So as N contains X, That is, as H contained in N, sigma X equals X for all sigma in H as well, because H is potentially small. Therefore, this means, by definition, X is in H prime. So, what do we got here? N prime is contained in H prime. Okay, not too shabby. So far, so good. What about this? L is contained in L double prime. Well, let's see what we can do with that. So, let's see where we E. Let alpha be an L. Now, L prime is a set of sigma in G such that sigma alpha equals alpha for all alpha in L. Right? So L prime prime, that is L double prime. Now remember, this is a group. This is back to a field. So this is all the V and F such that sigma V is V for all sigma in L prime. But notice that if alpha is in L, then alpha is fixed by any sigma in L prime, right? Therefore, alpha is in L prime, which is L double prime. Because since alpha is fixed by any sigma in L prime, by definition, it's in here. So, L is contained in L double prime. H is contained in H double prime exercise. That's not too bad to do. So I'll do, let's do F. And again, I'll probably just do one of them. The other one I'll leave as an exercise. Maybe I'll do the field one again. I really like the proof of F because it's slick. I'm kind of done with the definitions here. So let's see. I want to show that L is equal to L triple prime, right? So let me point out that L is contained in L double prime by part E. So I will apply, and let's see, what is L? L is a field, so I'll apply C. And I will get L prime is contained in L double prime prime. Because part C says, whoops, no, it doesn't. Got a little carried away there. Let's apply C to this. Field is contained in field, like in part C. So the prime is contained in L prime. So I get L triple prime is contained in L prime. That is just applying number E and number C. How about the other containment, right? I wanna also show that L prime is contained in L double prime, right? But notice L prime is contained in L prime double prime. I feel so dirty by E again. Because what it says is any field is contained in its double prime. Oh, I'm sorry. It's actually this one, isn't it? Because L prime is a group. So by this part of it, L prime is contained in L prime's double prime. So L prime is contained in L triple prime. And so now we've got both containments. I love that little proof. It's kind of slick. You almost feel a little dirty, like you're getting away with something there. Okay. Let me make some observations here. So here's an observation. Now, suppose you have K and F. This is Galois. If and only if K double prime is equal to K, right? And this is, let's not make too much out of this. Let's think what K double prime is. That's K prime prime. And K prime is G. This was our first easy observation. So really what this is saying is this is just going back to the definition we had earlier. K over F, F over K, that is Galois, if and only if K is equal to the fixed field of G, right? So remember what this is. This is the set of everything in the field that is frozen by all of G. And it's Galois if and only if that's K. So that's all that we're saying here. More generally speaking, F is Galois over an intermediate field. So you can generalize this fairly easily. Here I'm going to take just a more general stance here, and instead of going all the way to the base field, I'm picking perhaps an intermediate field, E. F is Galois over E, if and only if E double prime equals E. And it's the same principle as up here. Now, if you remember from statement of the fundamental theorem of Galois theory, you might say, but Jim, you said that F was Galois, in the fundamental theorem it says F is Galois over every intermediate field. Yes, that's true, but we haven't gotten there yet. We haven't proved that. And we're going to prove that in the situation that we define for the fundamental theorem of Galois theory, that it is indeed the case that for every intermediate field, E double prime is equal to E. Okay, let me give you a following definition. definition, 14.2.9. Let's let K inside L, I'm sorry, let's let X be a subgroup of the Galois group, or an intermediate field extension. So let F be, I'll assume it's Galois here. Okay, I'm not going to assume that. An extension. And G equal to the Galois group of F over K. Of course, the Galois group always exists. It's just the automorphism fix K. I'm not assuming that it's Galois at this point. Let X denote a subgroup of G or an intermediate field extension. So this is just a generic notation for X might be a subgroup of the Galois group or an intermediate field between K and F. We say X is closed if X double prime equals X. It probably, from the lemma that we just talked about earlier, it probably seems like we're teetering on the border of this, right? I mean, what did we know? What did we discuss in the lemma? Well, we knew that we almost got that the intermediate stuff. We know that X is contained in X double prime. That's one of the things in the lemma. It's contained in its double prime. And we also got that and by the way, if you keep adding primes up here, X double prime is equal to X quadruple prime, and you can keep adding that one. This is the last one where things may fail, and it's special. That is, we say it's closed if you actually get equality for the double prime here. And this is going to be an important piece of it. Notice that in the previous lemma, so if you look back at the lemma that we just did, what it does is it gives a one-to-one correspondence. So we've already got this far. We've got a one-to-one correspondence between the closed subgroups of G and the closed subfields of F, given by E goes to E prime, right? So in a certain sense, we're almost there, right? Because what we've got is we've got what I said was going to happen and the fundamental theorem of Galois theory, at least in the case where we're talking about closed subgroups and closed fields. So there's a one-to-one correspondence between the closed subgroups and the closed intermediate fields. So from here on out, we're going to show that if F is algebraic and Galois over K, then all the intermediate fields are closed. And if F, so we're going to probably do it in that generality. And additionally, if you turn up the voltage just a little bit, so assume more than algebraic, assume that F is finite dimensional, then all the subgroups of the Galois group are closed. So let me give you the following. I'm going to keep following the lemma here. So lemma 14.2.10. So let me get this mouthful out. Suppose I have fields if the degree of M over L is finite, L is an infinity, then the index of M prime in L is bounded by this. So in particular, so here's something of note. In particular, if the degree of F over K is finite, then the Galois group is bounded by this. In particular, it's finite. Okay. This is going to take a little bit longer. So what I'm going to do, I'm going to come back to prove this, because this is the limit that I start with respect to fields. So let me give you kind of a companion lemma that we will finish up this session with. So, like I said, I'll come back to the proof of this 14.2.10 later. Let me show you the companion that we're going to use, and you'll see some similar, you'll see analogous themes here. Lemma 14.2.11. Let K and F be fields, and H and F be fields. And let's say that we've got H and N in the Galois group, subgroup of N, subgroup G, which is the Galois group. Right. I guess what that means is, yeah, if the index of N and H is finite, then we get inequality in the other direction. That is, H prime N prime is less than or equal to, so the degree of the field extension H prime over N prime is no more than the index of N and H. Not even H, H and N. There we go. Right. Okay, so that is actually, I think, a perfect time to stop. But notice that these are very similar in things, right? This starts from the point of view of starting with the fields and looking at this comparison here, where the group less than or equal to the field extension. This starts with the groups, and the field extension is less than or index to the groups. We're going to use this leverage to get the rest of the fundamental theorem of Galois theory. That is, close up the business about to close. And that will be good for now. I will see you folks at least by Monday.